It's great to be here. Can you guys hear me okay? Is this all working good? Okay, so today I'm going to tell you about some work that we've done imaging two-dimensional Wigner crystals. First, I would just want to say a few words about my collaborators and funding sources. This work that I'm going to show you is a very tight collaboration between my group and Feng Wang's group. I just want to be clear on that. And Steve Louie did the theory, and Alex Zettel's group helped us to make the devices. Here are all the students and postdocs who worked on it, but I would like to call out the names of two people in particular, Hongyun Lee and Xiaowei Li, who really did all the STM measurements. They did the heavy lifting and analyzed the data, and you know, they did the heavy lifting. The crystals, the transition metal dichalcogenide crystals came from Arizona State University, the group of Tange, and our boron nitride came from Japan, the group of Taniguchi and Watanabe. And our funding came from the Department of Energy, Army Research Office, and National Science Foundation. So here's what I'm going to talk about. This is an introduction, or I'm sorry, the outline. And I'll say some introductory words about Wigner crystals, what they are, and moire materials. And then I'll say a little bit about how we're able to use scanning tunneling microscopy to explore gate-tunable moire devices. And then I'll talk about a new sensing layer geometry that we've used to image Wigner crystals. So let's start out with what is a Wigner crystal? Well, a Wigner crystal it's a crystal of electrons. So if you can get the electrons to crystallize like ice, that's what a Wigner crystal is. And it's actually kind of tricky to do. Most electronic systems are not Wigner crystals. In most electronic systems, the kinetic energy of the electrons is dominant, and the electrons are like a gas or a liquid. For example, in metals, the electrons are like a liquid. But if you can engineer an electronic system so that the potential energy is dominant, then you can engineer it so that it costs too much energy for the electrons to move around, and so they freeze. And when I say potential energy, I just mean the electrostatic Coulomb repulsion between electrons. And in that case, we call that system a Wigner crystal, and it's an insulating phase. The most important parameter that determines whether an electronic system becomes a Wigner crystal is this gamma parameter, which is the ratio of potential energy to kinetic energy for the electrons. If this ratio is around 1, then the electrons form a fluid or potentially gas phase. But if this ratio, if the potential energy is much bigger than the kinetic energy, that's when you can get a Wigner crystal. So let's just spend a moment talking about these two parameters. Let's start with the potential energy. That's the easiest one to conceptualize because the potential energy per electron of an electronic system is just going to be the Coulomb repulsion between an electron and a nearest neighbor. So it's this familiar expression that depends on the distance between the electrons. The kinetic energy is a little bit more complicated. There's two different regimes, the classical and the quantum limit. In the classical limit, the thermal effects are most important. But in the quantum limit, it's really the Pauli exclusion principle that matters. And so for today, for this talk, I'm just going to focus on the quantum limit. There's also interesting stuff in the classical limit, but I don't have time to talk about that. So let's consider the quantum limit. Let's consider a two-dimensional system of electrons where the electrons are confined to a two-dimensional plane like this. They just swim around in 2 dimensions. In this case, the kinetic energy is just, the electrons are all living in a band. We have the energy versus momentum, and so this red color represents the filled states of the band. Those are the electrons. And the kinetic energy, to get the kinetic energy, we just integrate the energy from the bottom of the band up to the Fermi energy. And if you do that, then you can see it's pretty easy to show that the kinetic energy per electron is equal to this very simple, in 2 dimensions, it's equal to this very simple expression that depends on the mass of the electron and the average distance between the electrons, A. And so if we take that expression and combine it with this expression for the potential energy, then you can calculate pretty easily, you can very quickly calculate this ratio of the potential energy to the kinetic energy, and you can see that it's equal to the mass, it's proportional to the mass of the electron divided by the square root of the density of electrons. And so what that means is that if you want to create a Wigner crystal, then what you want is electrons that have big mass, and you also want it to be dilute. You want that density to be small so that that ratio gets big. But what is the ratio? What's the magic ratio at which you actually get this phase transition from liquid to solid for the electrons? That's actually more difficult to calculate. You need to do some really in-depth quantum mechanical simulations. But luckily, some folks did it back in 1989, Kanatar and separately, and others as well. And they predicted that Wigner crystals in 2 dimensions should occur when this ratio of potential to kinetic energy is around 34. So 34 is the answer, the magic number. All right, and so now just to really get this notion clear, let's do a little thought experiment for a moment. Let's consider a one-dimensional box like you learn in undergraduate quantum mechanics, and let's put 6 electrons into that one-dimensional box, and those 6 electrons are going to sit in these 3 lowest levels, 2 electrons each, and we learn this in undergraduate quantum mechanics. And if I now stretch that box, then you know what's going to happen. You learn in undergraduate quantum mechanics the energies go down. I stretch it more, they go down. But the part that you don't learn in undergraduate quantum mechanics is that if you keep on stretching it, eventually the Coulomb repulsion is going to dominate over the kinetic energy, and you're going to have a phase transition, and the electrons are going to do that. So this is what I'm talking about. This is the Wigner crystal right here. And so this is what happens when the potential energy dominates, the electrons just freeze like that. So this becomes the wave function. Okay, so have people actually done this and studied this in real life? Well, the answer is yeah, people have been studying this for a while, and the system that people have studied the most is semiconductor interface systems, such as gallium arsenide sitting on a layer of gallium arsenide sitting on top of a layer of aluminum doped gallium arsenide. Then what you find is because of band bending at the interface, the electrons are trapped at the interface, and you get a 2-dimensional plane of electrons. They cannot move perpendicular to the interface, but they can move parallel to the interface. And in this case, what happens is that the electrons occupy this 2-dimensional band at the interface, but there's a problem because the mass of those electrons is pretty small, and so if you look at this ratio of potential energy to kinetic energy, it's kind of small. And so it's really hard to get a Wigner crystal for this system. And so what people do is a trick, and the trick they do is to turn on a magnetic field, because that makes the electrons go in circles, Landau levels like you see here, and it causes that nice dispersive band to flatten out into Landau levels. And in the language of solid state physics, what we say is that these Landau levels have a very heavy mass because they're flat. And what that means is that the mass is big, so now this ratio gets big. And that's good, because now it's easier to get a Wigner crystal. And in fact, people have seen lots of evidence for Wigner crystals in this system under these conditions since the 90s. My favorite experiment is when they make the Wigner crystal move by applying, they have evidence that the Wigner crystal moves by applying lateral electric fields, which I think is kind of cool. But what happens when you turn the magnetic field off? B equals 0. Then is it possible to make a Wigner crystal? Well, people have evidence that they can do it then as well, but the trick now is to put the Fermi level into the valence band because now the holes have a big effective mass, and so that makes this ratio larger, and it's easier to get a Wigner crystal. And there is some evidence from Yoon and co-workers that they have evidence that they've seen a Wigner crystal under these conditions. Here they've measured resistance as a function of temperature, and they see evidence for a metal insulator phase transition as they increase or decrease the density, as you can see. But a problem with this kind of measurement is that there are other things that can give you a metal insulator transition. For example, if you have defects, like these circles with the little plus that represents defects, the electrons can bounce off the defects, and that can create localization. And localization can also give you a metal insulator transition. And so it's hard to know from simply doing a resistance measurement, it's hard to know if your electrons are doing Anderson localization or whether you have a Wigner crystal. Now, if you could visualize the electrons, then you could tell the difference right away. But if you're just performing transport, then it's hard to know which of these is happening. So I want to show you the data where we visualize the Wigner crystal. But before I do that, there's one other question that I want to address, which is, what's the effect of a lattice? What happens if I put the electrons into a lattice? How does that change this picture? And that's pretty common in solid state physics. We often put electrons in lattices. And as a solid state physicist, one of our favorite models is the Hubbard model. The Hubbard model is so nice. We love the Hubbard model because it's so simple, and yet it has a lot of rich physics. And it was invented in 1963, and it's just simple to write down. You have electrons in this periodic potential, And there's really three major parameters that that are important for the Hubbard model. You have this T parameter, which is the hopping amplitude, the amplitude for an electron to hop from one unit cell to the adjacent unit cell. You can think of that as the kinetic energy per electron. That really represents kinetic energy. Then you have this other parameter, U naught, which is the energy of double occupation for a unit cell. So if I put 2 electrons in that unit cell, there's a Coulomb repulsion. It costs that much energy to put in that second electron. And the third parameter is this density of electrons and the number of electrons per unit cell. So if you have the density of electrons less than 1, then what happens is lots of these cells are empty. There's no electrons in them, and so the electrons can move around very easily. They do not have to pay the price of double occupancy, and so the system is typically metallic. On the other hand, things get a little more interesting when the density of electrons is 1 electron per unit cell. In this case, the electrons have to pay the cost of double occupancy to move around, and things are a little trickier. However, if the kinetic energy is much bigger than the potential energy, like in this regime, then the system is typically metallic because the electrons can move around. They don't care. They don't worry about the cost of the Coulomb potential. But if the energy of double occupancy is much bigger than the kinetic energy, then the electrons cannot move along. They can't move because it costs too much energy. In this case, the electrons are frozen. And so you might think to yourself, hey, that's a Wigner crystal. But it's not a Wigner crystal. We call that a Mott insulator. And the reason it's not a Wigner crystal is because it's really the on-site energy of double occupation that's freezing the electrons. It's not the long-range Coulomb interaction. So the long-range Coulomb interaction, people didn't really think about for a while, but people have thought about it. And one of the first people to think about it was Hubbard himself back in 1978. Hubbard extended his model into a new model that we call the extended Hubbard model. And he introduced this parameter, Uij, which is the long-range Coulomb interaction between electrons that are in different unit cells. And so things can get a little more interesting when we include this long-range Coulomb interaction. Now, for example, if we have n less than 1, we still have empty spaces in our lattice, but now there are some different physics can happen. If the kinetic energy is really big, much bigger than the long-range Coulomb interaction, then the system is still metallic because the electrons can just move around. They don't care about the Coulomb interaction. But if that long-range Coulomb interaction is bigger than the kinetic energy, then some problems occur because now the electrons have to pay that Coulomb interaction to move around. And under some conditions, we can get new insulating states. For example, even back in 1978, Hubbard predicted that if the density of electrons is equal to a rational fraction, P over Q, then we should get a crystallization of the electrons. And that result is actually more intuitive than it sounds, I think, if you take a look. For example, suppose n equals 1/3, 1 electron per every 3 lattice sites. What Hubbard predicted is that the electrons would freeze into this pattern. And that kind of makes sense because that's going to minimize the electrostatic interaction. If n equals 1/2, then he predicted that they would freeze in this kind of a pattern, and for n equals 2/3 like this. You can see the pattern. The electrons are just spreading out to minimize the electrostatic interaction, and they're freezing into a crystal. These are Wigner crystals because the crystals are frozen by the long-range Coulomb interaction, but they're in a lattice, and so we call them generalized Wigner crystals. So this is what a generalized Wigner crystal is. And so the question then becomes, how do you make these kinds of things in real life? How do you actually see this kind of physics? Well, people have postulated lots of different things. Some people believe that you can see this kind of physics in complex oxides and other materials. But there's a new material that people have been studying where we can see this kind of physics. And that new material is the one that I want to focus on today. And that is moiré heterobilayers. And so now we get into the topic of moiré materials. So what is a moiré material? Well, you might have heard of moiré materials. I think most of you probably have heard of it. You take a two-dimensional material, you take another two-dimensional material, and you put one on the other. And if you twist them, then you can get a moiré interference pattern. Well, I'm not going to talk about that. Instead, what I want to talk about is if you take two-dimensional materials, and if they have a slight lattice mismatch, then if you put one on top of the other without twisting it, then you also can get an interference pattern like you can see here. You see there's a new periodicity. That's the moiré periodicity. And that moiré periodicity gives you a new energy landscape. And what you get is an energy landscape that looks a lot like the extended Hubbard model for certain materials. For example, if an electron is sitting in one lattice site, then there's a hopping amplitude for it to jump to the other lattice site, a hopping amplitude T. That represents the kinetic energy. Also, if I put 2 electrons into one unit cell of this moire periodicity, then there's an energy of double occupation. We can call that U naught. And there's also a long-range Coulomb interaction. If I have 2 electrons in adjacent cells, then there's going to be a Coulomb repulsion between them that I can call Uij. And I just want, and lots of people have done theory on this kind of system. Here I list some theory papers. People have made predictions. And I just want to remind you that the interesting physical limit is when this long-range Coulomb interaction is bigger than the kinetic energy. That's when we might be able to see this freezing of the electrons into this generalized Wigner crystal phase. And in fact, people have seen evidence for that experimentally. There's been a number of different groups. One of the first groups was Feng Wang's group and his collaborators. They did this really nice experiment where they measured the capacitance of a moire hetero bilayer made out of a single layer of tungsten diselenide put on top of a single layer of tungsten disulfide. And then they measured the capacitance while shining light in this really clever way, and they saw evidence for insulating states occurring at fractional filling factors such as n equals 1/3 and n equals 2/3. 1/3 means 1 electron for every 3 moire unit cells. 2/3 means 2 electrons for every 3 moire unit cells. And they postulated, or they hypothesized, that this is due to the formation of generalized Wigner crystals where the electrons are freezing into these weird patterns that I'm showing you down here. Those are funny patterns that minimize the electrostatic interaction, like what Hubbard had predicted. Another group that saw similar kind of behavior was Kin Phi Mac's group and Ji Shan's group as well. They did this very clever exciton technique, and they saw evidence for Wigner crystal, generalized Wigner crystal formation at a variety of different filling factors that you can see up here. They hypothesized that these insulating states were occurring because the electrons are freezing in these funny patterns that you see here. Another group was Young Tao Tsui at Riverside, who used microwave impedance microscopy to see generalized Wigner crystal behavior. And I just want to mention that this is a technique that was pioneered here in Ziek Shen's lab. And in fact, Young Tao Tsui is one of Ziek Shen's former students. And his group saw some beautiful Wigner crystal behavior at different filling factors. And they also hypothesized that it's coming from these different electron patterns forming in their 2-dimensional sample. And other groups as well have seen it. But something that I want to mention is that all of these groups are hypothesizing that the behavior they see is due to these different electron patterns. But I'm an STM guy, and so I don't believe none of this until I can see it for myself. Because how do you know that the electrons are actually forming these patterns unless you can see the patterns? There's lots of things that create gaps, energy gaps, and I don't believe it until I see it. So that brings us then to the next question, which is how do you actually visualize a 2-dimensional Wigner crystal? How could you actually visualize these electrons and prove that they really are forming these weird patterns in real space? How do you do that? It's not totally obvious, but if you want to see a 1-dimensional Wigner crystal, that has been done. In 2019, Shahal Alani of the Weizmann Institute did a beautiful experiment where he imaged a 1-dimensional Wigner crystal living inside of a single carbon nanotube. His group brought another carbon nanotube as a sensor, and they saw the Wigner crystal. Here's their data. These bumps, each bump here is a single electron. That's a Wigner crystal. So they saw it. So that's quite beautiful. But this technique does not have the resolution to see the 2-dimensional Wigner crystal that I'm talking about. The resolution is off by at least an order of magnitude. So what technique does have the resolution? Well, one technique is the scanning tunneling microscope. That's my favorite technique. And so what an STM is a sharp metal needle that you scan across a surface, and you suck electrons up through the tip, and you measure the current, and that process allows you to observe structures with atomic resolution. So that certainly has the resolution to see the Wigner crystal in this moire hetero bilayer where the period is about 8 nanometers. So it certainly has the resolution, but there's a bunch of problems with the STM. For example, you have to gate the electrical device, and I'll explain what that means in a second. You have low temperature contacts, you have the perturbation of the Wigner crystal by the STM tip. These are big challenges, but what I want to tell you about today is how we overcame these challenges to actually image Wigner crystals with an STM. And so that's what I want to explain, is how we did these things. So let's start with the very first one, gating the device. What does that mean? Well, to explain what that means, first I just want to show you a cartoon of an experiment, of an STM experiment without a gate. This is sort of conventional STM. You take your tip, you put it on top of a material you're interested in looking at, such as a semiconducting moire heterobilayer, and you hook a wire to it with a battery and you measure the current. And what's happening here, microscopically what's happening is that you have the density of states of the tip and you have electrons in the tip. The red color means filled electron states. They tunnel from the tip into the semiconductor. This is the density of states of the semiconductor surface. This is the valence band filled with electrons. The conduction band is empty. And then you can measure the electronic structure of your surface by tunneling electrons from here to there. That's a conventional STM tunneling experiment. And lots of people have done that on moire heterobilayers. And here I list a bunch of groups. That's not my group. These are other groups that have done this experiment on moire heterobilayers. But the problem with this experiment is that there's no charge carriers in the moire heterobilayer. In a conventional STM experiment of this nature, there's no charge carriers because the conduction band is empty. There's nothing there. See, nothing is in there. It's empty. Also, the valence band is empty because there's no holes. No holes in the valence band, no electrons in the conduction band. It's empty. There's nobody home. So there's no Wigner crystal. So to get the Wigner crystal, we have to put electrons into that conduction band. And so how do we do that? Well, one way to do it is to gate the system. And what a gate is, it's just a metallic electrode that you put under your sample. You put an insulator and a metallic electrode. As you can see, it's just a capacitor. You just build your sample into a capacitor. You put a voltage across it. You charge up the capacitor, and that charge goes into the conduction band. And that's where your Wigner crystal is. That's how you can get the Wigner crystal. You're putting electrons into the conduction band. Those electrons are going to create your Wigner crystal. So this is what you got to do. So that's what we did. And so now I'll explain how we did it. The semiconducting moire system that we used was this. We took a single layer of tungsten diselenide and we stuck it on top of a single layer of tungsten disulfide. Why did we pick that combination? Because that's what everyone else did. All right, it worked for them, hopefully it worked for us. Okay, and so if you do that, then what happens is you have a 4% lattice mismatch between these two materials, and they form a moire structure, as you can see here. And it turns out that for every moire unit cell, there's 3 different stacking sequences. In one region, you get what we call the AA stacking sequence, where the 2 lattices are right on top of each other like this. Then we have these 2 B regions. In one region, the top selenium atoms are sitting on top of the tungsten atoms below. And in the other region, the tungsten atoms on top are sitting on top of the sulfur atoms below. So there's these 3 regions. The only thing that I want you to remember is that this is the most important one, because that's where the electrons go. The B region, where the selenium atoms are on top of the tungsten atoms, that's the most important one. That's where the electrons are going to go. And the electronic structure of this heterobilayer has been calculated by Stephen Louis' group. With Nake did it. And this is the band structure they calculated. So this is the energy versus momentum eigenstates of electrons living inside of this heterobilayer. It's pretty complicated, but all these details don't matter. The only things that matter is that we have a 2 electron volt band gap. And also here, we have this nice flat conduction band and a nice flat valence band. So when we add electrons to the system, the electrons go there. And so that's the only thing you have to remember. There's a nice flat band. That's where the electrons go when we gate it. That's where the Wigner crystal is going to live, in those states. So this is the device that we made. We took a silicon wafer with silicon. The silicon is doped, so it's metallic, a silicon oxide. We put a layer of BN on top of that, then a single layer of tungsten disulfide, and a single layer of tungsten diselenide on top of that. And then we took a single layer of graphene and we put it on top of that. But a trick that we did was to cut slots into the graphene. And when we did our STM experiment in those slots. And that turned out to be the most important thing of all. It took us years to figure out how to do this because we could not make electrical contact. This is our big trick. This is the technical innovation that made it all possible, was making that funky contact for us. That's how we were able to make it work. Okay, so here's an optical micrograph of our device. You can see the 2-dimensional material. That's the electrical contact. That's the STM tip. It's hard to see much in this micrograph, so let's zoom in on that region right there. And here's an AFM image. Now you can see the stripes. Those are the graphene stripes and the bare TMD between them where we did the experiment. Now let's zoom in some more. And now you can start to see the moire pattern. This is an STM image. You can see that periodicity. That's the moire pattern on the TMD. But you can still see the moire pattern through the graphene. Now let's zoom in even more. And now you can see the moire pattern quite nicely. So that's the periodic moire pattern. Now remember I said that there are 3 stacking regions. That's the AA region where the 2 lattices are on top of each other. These are the 2 B regions, and that's the one I told you to remember where the selenium atoms are on top of the tungsten. So these 3 stacking regions are periodic across the surface in this moire pattern like that. Now we can do what we call STM spectroscopy on this surface, and what we do is we take our STM tip and we put it on right above the material, and we measure the differential conductivity of the STM tunnel junction, this quantity, as a function of bias voltage between the tip and the surface. And what we measure, you can think of it as the density of states of the material. It's really the local density of states, but you can think of it as the density of states. And what we see, for example, is that in this energy range, there's no states. That's the band gap of the material. It's 2 electron volt band gap. And over here, you can see the valence band states. And over here, you see the conduction band states. And a nice trick that we can do with the STM is we can tune to a particular energy, let's say the valence band edge right there, and we can measure the wave function of electrons living at that energy. And that's what you see here. We call that a DIDV map. And notice how only one region is lighting up. This is the same region as here. Now notice that the only region that's lighting up is this one, the B region where the selenium is on top of the tungsten. That lights up because that's where the electrons like to go. So that's the only important site. And so what that means is that the energy landscape of this moire superlattice is, you can think of it as being each of these B regions forms a little potential minima, and we get an egg crate potential, and the electrons like to live in the little minima formed by that periodic B region. So we get this periodic egg crate potential. And by doing these types of STM experiments, I won't go into all the details, but by doing these types of experiments I just described, we are able to extract the energetic parameters of this moire energy landscape, this extended Hubbard model. For example, we're able to figure out experimentally that this hopping amplitude is half a millivolt. So you can think of that as the kinetic energy per electron. And we're also able to figure out experimentally that this long-range Coulomb interaction of electrons on 2 adjacent lattice sites is 25 millivolts. It's harder for us to measure this energy of double occupancy, but we are able to determine that it's bigger than this long-range one. So we think it's in the 50 to 100 millivolt range. And so this is good, because what this means is that what we see from this is that the Coulomb interaction, the long-range Coulomb interaction, is much bigger than the kinetic energy. And so that puts us into an interesting regime where it might be possible to actually see the generalized Wigner crystal. So that's good. So that means that all we got to do then is to gate our sample, fill it with some electrons, and take a picture of it. And so that's what we did. So here we turned on this gate voltage down here, and we then we doped some electrons into our hetero bilayer, and we chose to dope n equals 1/2, meaning 1 electron for every 2 moire lattice sites. So we expect the pattern of electrons to look something like this little cartoon. That's about 10 to the 12th electrons per square centimeter. And then we took a picture of it with our STM, and what we saw was nothing. It didn't work. Fuck. Didn't work, of course not. Nothing ever works the first time, almost nothing. So we saw nothing after all that work, it didn't work. After all that, it didn't work. But then we thought about it and we realized why it didn't work. The reason it didn't work is because what's happening is that the tip, to image with the STM tip, there's electrostatic charges. For example, if you bring 2 materials that have different work functions close to each other, there's going to be some charge transfer between them, and there's going to be some charge difference. And that charge difference is going to create electric fields. And those electric fields are going to push away the electrons. So if I try to image electrons, I'm trying to image them, but I'm pushing them away as I move the tip. And so that's why we couldn't see them. We're pushing them away. So we realized that in order to see those electrons, we had to do something different. We had to protect the electrons from the tip, from the electrostatic field of the tip. And so to do that, we invented a new experimental technique that we call the sensing layer technique. And to understand that, let's first consider the old design. The old design is to have our sample here and a back gate and an insulator and bring the STM tip down on top of it. That's what I showed you before. But that didn't work for us because the tip, the electrostatic interaction of the tip and the electrons is too great. So what we did, the new design, is to protect the material with one more insulator. We put a 5 nanometer thick layer of boron nitride on top of our moire hetero bilayer, and then we put a single layer of graphene on top of that. And that single layer of graphene on top we call the sensing layer, and it does a lot of good things. It has a lot of good properties. For example, it gives us a top gate. Now we have another gate, and that 2 gates are always better than 1. Also, what happens is, what we can do now is we can sense. The idea is that we can sense the electrons in the moire hetero bilayer by how they alter the electronic structure of the graphene. So the idea is that the STM tip will now image the graphene, and we will look to see how the graphene electronic structure changes due to the electrons down here, and that way we can see the electrons underneath, see what they're doing. And this graphene, another benefit is that it's going to help screen out the electric field of the tip. Not completely, but enough so that the tip does not destroy the Wigner crystal underneath it. So that's the idea. And having these 2 gates is quite nice because now we can independently control the electron density in the graphene. So we can put the Fermi level near the graphene Dirac point, which gives us the highest sensitivity. And we can also control the Fermi level in the moire hetero bilayer, and that's where we want to put it, right there. So the red color is electrons. So this is how we want to make a Wigner crystal. We just want to put a few electrons right there at the bottom of the conduction band. That's the idea. That's where we hope to find a Wigner crystal. So here's a picture of the device. Not a picture, but that's a more detailed cartoon. And you can see how we have our moire hetero bilayer here, and we've sandwiched it between boron nitride on top and bottom. We have our silicon, doped silicon backgate. We have our sensing layer of graphene on top. So the first thing we did was to take an STM topograph of that top layer of graphene, and this is what we saw. That's the moire pattern of the underlying moire hetero bilayer. And that actually surprised us. We weren't expecting to see it because the hetero bilayer is sitting 5 nanometers underneath all of this boron nitride. We didn't expect to see the moire pattern, but we did. We saw it very, very clearly. And here we can zoom in on it, and now you can see these different stacking regions. That's the AA stacking region. This is these 2 B stacking regions. That's the one we care about the most right there. And so this is a unit cell of the moire pattern. And so then what we did next, the idea next then is to tune these voltages of our gates so that we can put the Fermi levels where we want them. Remember, we want the graphene Fermi level near the Dirac point, and we want the Fermi level of the hetero bilayer near the band edge here. And so then the idea is to tune this backgate voltage so that we can change the number of electrons here so that we can change the density of electrons and tune through these different Wigner crystal structures. That's what we wanted to do, and take a picture of them. So that's what we tried doing. And so let me show you the results. So here, the first one that we looked at is n equals 1. So n equals 1 means that there's 1 electron per moire unit cell. So we tuned our gates so that we could get to n equals 1, and we know how to do that because we know the capacitance of our device, so we know how much charge is going everywhere. So we could do that without too much trouble. And then we use the STM tip to take a picture of the electronic structure of the graphene layer. We took what we call a DIDV map, and the electronic structure of this graphene top layer is here. This is what we measured. Now what you're seeing here is all these white blobs, and each of these white blobs represents a single electron underneath. So that white blob that you're seeing here is the effect that the electron underneath has on the electronic structure of the graphene. So what we're seeing then, this periodic pattern represents a periodic pattern of the electrons underneath in the moire hetero bilayer. And because we have 1 electron per every moire unit cell, we expect this periodicity to match this periodicity, and indeed it does. But there's a difference, and the difference is that if you look at the centers of all of these electrons, they do not lie at the bright spot, because that's not where the electrons are. Instead, they lie here in that special stacking region, the B stacking region, the one I mentioned. So that's nice, that's consistent. We can also take a Fourier transform of this structure, and there's the Fourier transform. You can see this hexagonal lattice structure. What you're seeing here is the smallest reciprocal lattices of this lattice, which matches the Moiré lattice structure. So that's consistent. So what we did then is we tuned this backgate voltage to reduce the number of electrons in our heterobilayer. We reduced it to n equals 2/3, 2 electrons for every 3 Moiré unit cells. And when we did that, we saw a completely different pattern. We took an image of the graphene, and now, instead of a triangular lattice, we see a honeycomb lattice. See? That's a honeycomb lattice. Every blob here, every periodic blob that you see is representing a single electron underneath in the heterobilayer. So now the electrons have rearranged themselves into a honeycomb lattice. And if you take a Fourier transform, you can see it has a completely different structure than the previous lattice. So by simply changing the number of electrons, we get a completely different electron pattern. Then we reduce it even further to n equals 1/3, 1 electron for every 3 unit cells. And now what we see is a completely different lattice. Now it's back to a triangular lattice, but it's a very dilute triangular lattice. It has a much bigger lattice constant than the original one. So now we have, and that makes sense because now we have only 1 electron for every 3 Moiré unit cells. And if you take a Fourier transform of it, you notice that it's the same Fourier transform, which is kind of funny. Do you know why? It's because they're inverses of each other. So it's kind of funny. And that's why you got to take a picture of the real space image. Fourier transforms, it's not good enough. Got to take a picture. The real space tells us more than the Fourier transform in this case. Then we did n equals 1/2. So now we increased the electron density to n equals 1/2, 1 electron for every 2 Moiré unit cells. And now we see stripes. We see a striped pattern. And you can see how we see stripes, and the lattice constant is longer in this direction and shorter in this direction. And that's reflected in the Fourier transform, which is completely different than the other patterns. So what we're seeing is that as we change the electron density in the heterobilayer, the electrons are arranging themselves into these different shapes. And it just happens to be exactly the shapes that those other guys thought. So they were right. But, you know, somebody had to check. We had to see if it was right. So now we can see it. So, okay, so now I believe it. All right, now I actually believe in generalized Wigner crystals. Okay, so that's what we were able to do. But now the question is, what more can you do with this? What about the original thing that I was telling you? Before when I was introduced this topic, I told you how just electrons without a lattice should be able to form a Wigner crystal. So what happens if we take away the lattice? Can we then see the Wigner crystal? I just showed you how we can see the generalized Wigner crystal in the presence of this lattice. But what happens if we take away the lattice? Now can we see the electrons crystallize without a lattice? So they should. The predictions are that if we reduce the density, they should crystallize. So that's what we went after that, to see if we could see that. And so to do that, we looked at single layer tungsten disulfide. And here I show the band structure of a single layer of tungsten disulfide. This is the energy versus momentum, and this is the conduction band edge right there. And so to make a Wigner crystal, all we got to do is put some electrons right there into that band edge, and if we put just the right amount, then they should crystallize. And what is the right amount? Well, we know from the theoretical predictions that this magic number, gamma, is 34, the ratio of potential energy to kinetic energy, and we know the mass of electrons in that conduction band. So if we work backwards, then we can see that the density of electrons should be about 10 to the 11 electrons per square centimeter. And so that's all we got to do, is put 10 to the 11 electrons per square centimeter right there and take a picture of it, and we should see a Wigner crystal. And in fact, there is evidence for this from optical measurements. These guys, Smolensky and coworkers, showed using optical techniques they have good evidence for Wigner crystal formation in single layers of moly disulfide, which is a very similar type of material. So if it worked for them, it should work for us. So we went after this by building this type of device. This one right here. And so what we did was we took a single layer of tungsten disulfide, we sandwiched it between 2 layers of boron nitride, we put graphite underneath as the backgate in this case, and then we put a single layer of graphene on top as the sensing layer. And so really what this device is, it's really just 2 capacitors, one on top and one below. And what the idea, just to remind you, is what we want to do is change the number of electrons in the single WS2 layer, and we want to image the effect that these electrons have on the graphene above, and want to see if we can image those electrons below by looking at how they alter the electronic structure of the graphene on top. That's the idea. So we did that, and this is what we saw. Here I show a DIDV image of the top graphene layer for when we put a density of electrons in that WS2 layer of 2 times 10 to the 10th electrons per square centimeter. And what we see is really nothing. It's not very interesting. There's nothing much going on. These two dark regions, those are defects. These bright regions are defects, and so there's not much going on. So then what we did was we ramped the electron density by tuning our gates from 2 times 10 to the 10th electrons per square centimeter up to 4 times 10 to the 11th electrons per square centimeter, so we could go through that region where we would expect to see the Wigner crystal. And so then we saw some interesting stuff. And let's see, I have a little movie. Let's see if I can make this play. What I want to show you is a little movie where we can, you can see how the electronic structure of the graphene layer evolves continuously as we continuously increase the density of electrons. And what the movie looks like, I just want to prepare you for it. It's going to blow your mind now. No, it's no big deal. So you see these little marbles. To me, it looks like marbles under a rug, and the marbles are kind of rolling around as we add more and more electrons. And so this is what it looks like. Okay, now we're adding more electrons. You can see all those like marbles rolling around, and then they disappear. Why are they disappearing? Let's play it one more time. See them. We're increasing electron density, increasing, and then they're gone. Why are they gone? So it's hard to understand what a movie is doing. So here are stills from the movie. And so here I show the images from the movie as I increase the electron density from 4 times 10 to the 10 now to 1.3 times 10 to the 11th. And what you can see, what we believe is happening is that every one of these bright spots here represents an electron underneath, and that bright spot is how the electron underneath is affecting the graphene layer electronic structure. So we believe that we're seeing the electrons underneath, and we believe that this is a Wigner crystal, and as we increase the electron density, the lattice constant of the Wigner crystal is shrinking. And then as we keep increasing the density of electrons, the Wigner crystal disappears. Why does it disappear? Well, we believe that it's melting. We believe that we're imaging quantum melting of the electron crystal. That's what we think we're seeing here. But how do we know? How do we know that that's what's really happening? It's hard to know in physics, you know, if you're seeing what you think you're seeing, right? And so we're not absolutely sure, but we have some additional evidence that supports this interpretation. One way that you can check this interpretation, for example, is to count the electrons. What we can do is we can count the number of electrons, these little bumps. We can count them, and then we know how many electrons are in our device because our device is just a capacitor, and we know that if we put a voltage across the capacitor, charge is equal to voltage times capacitance. We know that. So we know how much charge we're putting into that WS2 layer, so then we can just compare these two numbers and see if they are the same. If they are the same, then that's evidence in support of our hypothesis. So that's what we did. So the first thing we did is we know the capacitance of our device. So this is a plot of the density of electrons in the single WS2 layer as a function of backgate voltage. It's that red line. It's linear, as it should be, because it's just a capacitor. Now let's count the bumps. And so to count those bumps, what we did was we took a Fourier transform, and we get this ring, because there's some disorder there. But if we do an angular average of that ring, we see a little peak here, which is the average reciprocal lattice vector. And we can do a little bit of trigonometry to get the density. And then we can do this analysis for each of our images, and we get these blue dots. Those blue dots are the electron densities that we get from counting those bumps. And you can see that those blue dots are pretty close to the red line. And so for us, we're like, yeah, that's good. You know, we think that's pretty reasonable. And so we declare victory. And we think that these two numbers are pretty close. And so we think that this is additional evidence that we really are seeing a Wigner crystal in this material. And something else that we can notice is that this is where we believe we're seeing the melting. This is where we can no longer, in this regime that I highlight in green, that's where we stop seeing the lattice. It disappears. But if you look at the prediction from the theory, this gamma equals 34 prediction, they predict that the melting should occur at this lower density. So according to our data, it looks like we're seeing the crystal living to higher density than is theoretically predicted. And so why is that? Well, we don't know. But one possibility is because of defects. In fact, it has been hypothesized, or has actually been predicted. There are papers out there predicting that in the presence of defects, Wigner crystals should live to higher density. And so we think that that might be what we're seeing. Okay, so that's the end of my story, and I'm just going to conclude by saying that graphene sensing layers allow us to image two-dimensional Wigner crystals, and for the future we would like to see other things. For example, we'd like to better understand the melting dynamics of the Wigner crystal. We'd like to see if we could observe coexisting phases. We'd like to better understand the effect of defects. We'd like to see pinning and sliding, perhaps, of the Wigner crystal, and maybe even one day explore magnetism in Wigner crystals. Thank you.
Yes. What are the time scales associated with this measurement and the capacity and the charging, your voltage dial, essentially, in that movie and in general?
Well, the images take on the order of each image takes on the order of, say, 45 minutes for one of those images. You know, so we're talking about, you know, half hour to hour time scale for one of those images. You're saying, like, after it is true that if you ramp the voltage, then there can be some time constant, because, you know, we have big resistances, so there's, you know, RC time constants for the charging, but it's on the order of minutes. And is that?
Yeah. So if I can just confirm, because that's pretty amazing. In that movie, individual little marbles are essentially staying in the same location for hours. You know,
oh yeah, yeah.
Eventually delocalized.
That's right, and it's all at 4 degrees Kelvin.
Curious for the graphene sensing layer, if you know the relative twisting angle between the graphene and the HGN, to see if there's what the Moiré scale.
Well, you know, we don't want that Moiré pattern, you know, but often you know, we want the angle to be big, so that we get, you know, a really tiny insignificant Moiré pattern, and in this case that was the case. So but that's kind of random. We're not really carefully aligning that.
I would like to ask how robust is the Wigner crystal to different kind of perturbations? Let's say there is no uniformity in the Moiré structure, or there is like different strains. You know, like how does that affect the stability of these phases?
Okay, I can answer that question best for the defects help stabilize it for the single layer, but for the generalized Wigner crystal, those different phases were pretty robust. You know, we have to find a region where there's no, you know, where there's the defects, that's a defect-free region to see it. You know, if the defects are too dense, we're not going to see it. But, you know, if we get a couple hundred nanometers to a side, we can see it. But the one phase that was the most fragile was the n = 1/2. So the stripe phase. The other phases were much more robust. The stripe phase was very fragile. It only occurred over a very small range of parameters, and it was very sensitive to strain. And we could see the effect of strain by looking at the Moiré pattern. So the strain is going to affect that stripy pattern. So that is really the most sensitive, fragile one. But the other ones were pretty robust.
I want you to comment on why it is hard to find these two-dimensional Wigner crystals when, say, charge density waves, more conventional charge density waves, are fairly easy to visualize with STM. And don't require that for, you know, sensing layer, for example.
Okay, so you're saying why is it so easy to see a CDW and so hard to see the Wigner crystal?
Yeah, I think they're both, you know, nominally translation symmetry breaking electronic structures.
Okay, yeah, because we've done a lot of CDW imaging, and so the CDWs are pretty stable and easy to image. And when you look at a CDW, I mean, the CDW, I mean, you have this frozen lattice distortion, and then you have this distortion of all the charge in the valence band. So, and then you have this energy gap. And so, you know, so that is a pretty stable structure. Whereas for these Wigner crystals, you just have these electrons that, if you come in with the tip, if you push on it, these electrons can move more easily. And so I think one reason is because the density of electrons is much lower. You know, it's not like this huge, you know, it's not like this complete filled valence band. And so, yeah, I've never thought that through, but, you know, the CDW is really easy to visualize in comparison.
Oh, it's there, then here. Okay.
temperature limits that would, or the upper limit of temperature at which we could perhaps see these Wigner crystals? Keeping all the mechanical issues aside, do you think if one is to raise these temperatures above 4 Kelvin, apart from things like energy barriers, at what point of time should we start, or should we stop seeing Wigner crystals?
That's a good question. So okay, I mean, that question has been addressed. Some of the optical experiments have been looking at temperature dependence. There's a guy at Riverside who does optics. I forget his name, Joshua something or other. Somebody remember his name? He's a professor at UC Riverside. He's doing the optical measurements on Wigner crystals and has been measuring their temperature dependence. And I think he's been seeing it up to about 15 Kelvin. I think a question that you have to ask is, what's the energy of excitation? Because what's the how much energy does it take to take one of these electrons, out of the Wigner crystal and put it into, for example, an interstitial site? And that energy, we think, is on the order of 25 millielectron volts, and so that's actually pretty high temperature. But that, I think, is the relevant energy scale.
Okay, so when you're in your bilayer, first of all, when you send in the current, you're measuring the current from the tip through the graphene. That's your sensing, right?
Yeah.
Okay. So you said you were surprised to see then the moire pattern from the bilayer, but why? But you introduced 2 other moires. This is related to another question. You introduced there's another HBN to tungsten diselenide or whatever, and then there's a HBN to graphene. So why don't those show up at all in this image?
You're saying, why don't other moire patterns show up?
Yeah, they're closer to your sensing.
Okay. Well, first, this actually that's similar to the question that he asked. Yeah, and so first, in principle, we should see it. First we should see all these moire patterns if they're there. But what we believe is that the angle between the monolayer graphene and this BN layer is too big, because if that angle is big, then the moire, shrinks. Sort of, the moire becomes too dense and you don't see it. So that's what we think is happening there. And then you're asking, you're asking for the moire between the boron nitride and the WS2. Those guys have pretty different lattice constants, so I think that we don't expect that moire.
Okay. And then last question. Then, when you're changing the bias for the electron density.
Yeah.
What do you correspondingly change the tip bias, or do you, like the last stuff you showed on the model?
Well,
that should be independent of the
yeah,
truth, right?
The patterns are independent of the tip bias. Well, the geometry of the patterns is independent, but the contrast is not. So what we do is we tune the tip bias to get contrast, but the actual patterns, where the patterns are determined by the top gate voltage and the bottom gate voltage. So really what we're doing is we're sweeping the back gate voltage. We're altering the back gate voltage, and that's changing the density of electrons in this in this region right here. And that's independent of the tip bias. But we do play with the tip bias because we notice that the contrast can change a little bit, but it won't change the pattern.
You still have a question?
Do these crystalline states, can they exist for holes in the valence band?
Yeah, they can. But we can't always see them because sometimes we have difficulty. Sometimes we have difficulty biasing our samples. Certain samples we have difficulty biasing into the valence band, depending on the details of how we made the device. And so for this device, I'm pretty sure we weren't able to go down into the valence band. But yeah, it should totally work for holes. And the heavier the mass, the better. Heavier mass means you can then see a denser. Denser is better because if the Wigner crystal is too dilute, then it's hard, to see the periodicity. So heavier mass is better, then we can see a denser Wigner crystal.
You still, yeah. 1, 2, and 3. Back first. Yeah.
Well, I'm an astrophysicist. I'm out of my depth here, but just a curious question. Because we have a way to kind of image locations of electrons. I'm thinking in terms of the Heisenberg uncertainty principle. The uncertainty in momentum, uncertainty in location are limited, right? The del P times del X. If you've got the location of electrons pretty much nailed down, if you try to measure the momentum, would it come as highly uncertain because of the Heisenberg uncertainty principle?
Yeah.
There's a chance you could violate that.
I don't think we're violating it. I mean, one way of thinking about it is that the electron is in a wave packet, you know, and so one way of thinking about it is that there's a lattice of electrons. So just look at any one electron, and that electron is in a little trap. Because the electrons around it, let's say there's 6 electrons around it, they're forming like a box. And that electron is bouncing inside of that box, and that box, you could just think of it as like a simple harmonic oscillator potential. And so the electron that we visualize as this localized object is really living in the ground state of this simple harmonic oscillator potential. And so but that ground state is a wave packet full of many momentum components. And so those momentum components are consistent with the Heisenberg uncertainty principle.
Okay, yeah.
I was curious about the kind of filling fractions at which you expect to see generalized Wigner crystals in these electron-ice structures and kind of theoretically extend the Coulomb model. You know, in principle, the rational numbers are dense. So you know, there's find arbitrarily like good approximations to any rational number. But I'm curious, like, which rationals do you expect to see Wigner crystal states? And are there like differences for the different rationals? It seems like the small denominators are important. How does one think about that?
That's a really good question. What do you think's the answer?
It's your talk.
Sasha, I have no idea how to answer that question. That's a good question, though. I have no idea how to answer that question. I'm sure there is an answer, though.
I guess you even alluded to that. Like the 1/3, 2/3 states you said were like much more robust than the 1/2 ones, and like the triangular lattice. It's a very natural.
I guess. Okay. I guess just a simple-minded stab at how to even attempt to start answering that question would be to look at the energy of stabilization of these different states, and then you would have to start altering that fraction and start looking at the energy of these different fractions. And I would think that you would start to see energy barriers. I think that you would start to see a very complex energy landscape for these rational numbers, and you would have to explore that energy landscape to see which ones are more probable than others, and what's the trapping potential for one state versus another state. So I don't know that anyone's done that analysis that I know of, but I think that's a really interesting question. And certainly, like for example, if you look at the experiment of Qinfei Mek and Jishan, they saw many more fractions than we saw. And so there's some different experimental techniques, or maybe less perturbative. I'm not sure. I was really surprised at how many funky, weird rational numbers they saw, but we haven't seen. And maybe because our tip is perturbing, some very delicate ones. I'm not sure. That's an interesting question.
Okay. One here and one here.
So this is just like a curiosity. So in the last slide of data where you showed the charge density to calculate from the Fourier transform, it seems like there are some plateaus. So I was wondering if there is anything.
Are you talking about this, or are you talking?
No, the very last.
Oh, the single layer one.
Yeah.
This?
No. So when you take the Fourier transform of the data, and you have the average. Yeah, there's some plateaus in.
Here, this.
Yeah. So I was wondering if this can tell us something about the transition. Those plateaus where you change the backgate voltage, but it seems like the density doesn't change.
Yeah, that's a good point. But I would like to But that's but I'm not sure that our data is good enough to really address that yet. You know, I have to think about that. You know, if you know, we haven't done an analysis of those features to see how reproducible they are for different samples, different spots on the surface. But that's a good question. I mean, that's a good point that we should explore.
I imagine that would give you some information about the compressibility of the system, right? So.
Okay, let's make this be the last question.
So, Mike, very nice. If you look at the angular distribution of densities, can you look at any of the dislocations, disclinations in the crystal, or it's too early? Because there is a lot of stories about the different melting of two-dimensional crystals.
That's where we want to go. We haven't done that yet, and so what we want to do, we totally want to do that. So when I talk about the melting, this is what I'm talking about. You know, like sort of this kind of Kosterlitz-Thallos or TKKNY type of behavior. We want to see that. We haven't yet. I think we need larger defect-free regions to start to really be able to see that. But that's where we want to go.
Okay, let's thank the speaker again. Mike, why when the moray shrinks, you guys have good enough resolution, why wouldn't you see it?
Oh, the moiré of the graphene.
Yeah.
You mean of the graphene?
Yeah.